Okay, so here's some help with the test. In general, if you want individual, make sure I spelled that right. Individual, yeah, we go. Individual and small group help for chemistry or physics, you can email me and some friends at energytutoring@gmail.com. If I can't help, I can refer you to someone who can. So here is, I guess, the first main test, the first test of the spring semester of chem, or I guess the second part of chem. This question asks, what is the molarity of a solution of hydrochloric acid, which has this molar mass, which is 20.0% HCl by mass? The density of this solution is 1.18 grams per milliliter. So again, we have a situation where dimensional analysis can help us out. Let's see what's going on here. First reminder is that molarity is equal to moles over liters. It's moles of the solute over liters of the entire solution. It's different than molality. That's very important that you recognize the difference. We'll talk about that one later. So when something is 20% by mass, that means that of the, let's say there's 100 grams, if there is 100 grams of a solution, then that means that 20 grams of it is from the HCl that's dissolved in the solution, and the other 100 grams is the entire solution itself. So we don't know the mass of the solution. We also don't know the mass of the HCl, but we do have the density, which is going to help us be a conversion factor. So let's do that actually right here. We have 1.18 grams per milliliter, and this is for the solution. So we're going to say grams of the solution. So grams of the solution, and we're going to divide that by the 1 milliliter of solution. So again, this basically says that if we have 1 milliliter of this HCl solution, it's going to have a mass of 1.18 grams. So we can continue moving forward with this and asking ourselves, like, what do we even have? What do we know? Well, we want to convert, because we're looking for molarity, asking ourselves, which of these is going to stay? Look, HCl here and then solution here. Well, the volume of the solution is one thing we want to convert because we want to get molarity. So that's going to be 1,000 milliliters of any solution is equal to 1 liter of that solution. Now we have liters of solution in the denominators. We can circle this. Milliliters of solution are going to cancel out. We currently have grams of solution. We have the molar mass and we have the ratio here. So what we're going to do is we're going to use this as a conversion factor as well. Let me move this up. Those two pieces of information are just helpful. So we have 1.18 grams of solution on the left. What I'm going to do is I'm going to put grams of solution in the denominator so it cancels out. And I'm going to go from grams of solution to grams of the HCl. We actually have a ratio for that. It's right here. For every 100 grams of solution, 20 grams of HCl is dissolved inside of it. So currently we have this ratio, 20 grams of HCl per 1 liter of solution. I'm going to go do one more conversion factor. I'm going to get rid of grams of HCl. I'm going to go toward moles of HCl. That reason is important because, again, we want the moles of HCl in the numerator for calculating molarity, which is what we're asked for. So in the denominator, we have grams of HCl. And this is where we're going to use our conversion factor right here, which is the molar mass. 36.46 grams is the mass of 1 mole of HCl. So we have grams of HCl are canceled. Now we have moles of HCl in the numerator. Our units are going to make sense. So if we do our math all the way across, 1.18 times 1,000 times 20, and divide that by the product of 100 and 36.46, and you get exactly what the answer is, which is 6.47 capital M for molar. And that's the answer. Now, with a little bit of rounding error, I think that's probably why the answer is not exact, but there you go. So this one is a little bit trickier. Sorry if my computer is breathing really heavy. I'm uploading a video on YouTube. But right now we have it says calculate the molar mass of a non-electrolyte, which means it's not going to dissolve or break apart. The non-electrolyte component of antifreeze is 7.8 kilograms of it is needed to lower the freezing point of 10 liters of water to negative 23.3. You should know that water has a freezing point normally of 0 degrees Celsius, but when something is dissolved in it, it will have a lower freezing point and also an elevated boiling point. So the equation that comes to mind is that delta T subscript F, so the change in the freezing point, is equal to I times M times K subscript F. This equation basically says that the change in the freezing point of a solution is equal to the Van Hoff factor, which, by the way, since this is a non-electrolyte, I is equal to 1, so it's not going to dissociate into a certain number of particles. Sodium, for example, sodium chloride is NaCl. Under ideal conditions, it'll break apart into Na and Cl, and you have I equals 2. But a non-electrolyte will not break apart, so the I equals 1. M is the molality. Molality is not the same as molarity. Molality is the kilogram, or is the moles of the solute divided by the kilograms of the solvent, which in this case is water, and that's important to know. So molarity and molality are different. The numerators are the same, but the denominators are different. For molarity, it's liters of the solution. For molality, it's kilograms of the solvent. All that information is going to be helpful, as well as your knowledge of dimensional analysis. So let's get started on it. For this problem, it says calculate the molar mass, blah, blah, blah. So first you need to realize that you have certain pieces here. You have the freezing point depression amount. You have the Van Hoff factor. It's 1. You do not know the molality, but you do have the freezing point depression constant for this solution, for the water. So what we have here is that delta T is equal to I M K F. So plugging in everything, it's going to be a 23.3 degree fall, which is equal to 1, that's I. We don't know the molality, but we do know K, which is 1.86. Solving for this, we get that the molality is equal to about 12.53 kilograms per this would be moles. 12.53 moles of whatever the solute is per 1 kilogram of the water that it's dissolved in. This is going to become a conversion factor. So put that in your back pocket. Keep moving with the other stuff. Now we have 10 liters of water. So that's going to be important to write down. 10 liters of water is going to go here. 10 liters of H2O. That's our solvent. So we already see something in common. Put that over 1, and we can convert our liters of water into kilograms of water. Now, that's just one leap. If you want to make that leap, you can also do it through grams and milliliters, but 1,000 grams is a kilogram and 1,000 milliliters is a liter. Turns out that because of that, 1 kilogram of water has a volume of 1 liter. So that's basically, I just used density. I guess I could write it all the way out. I guess I'll do that just so you can see it from the pure part of it. So first I'm going to go from liters of H2O to milliliters of H2O, and then I can go from milliliters of H2O to grams of H2O, and then from grams of H2O to kilograms of H2O. And you'll see why the thousands cancel out. You know, there's 1,000 milliliters in 1 liter, and the density of water is given to us as 1 gram per milliliter, and there are 1,000 grams in 1 kilogram. So the thousands cancel out and all that stuff, and you end up currently with kilograms of H2O. Notice how that's actually a good thing, because we can continue with our dimensional analysis. So let's get rid of that circle because we don't actually want to stop there. So continuing with the dimensional analysis, we want to put kilograms of H2O in the denominator. And we have, like I said, we're using this as our conversion factor. So kilograms of H2O, we want to go from kilograms of H2O to moles of the solute. This is the molality. Solute. So this molality is actually a conversion factor now, because it says that 1 kilogram of H2O has 12.53 moles of the solute dissolved in it. So you have to first find the molality in order to use it as a conversion factor in your dimensional analysis. Now, if we were to stop the problem here, we would have moles of the solute. But remember, moles is not the answer that you're looking for. You're looking for grams per mole. So we need to use this. Let me see. Yeah. So there's a couple ways you can do this. I personally prefer to just calculate this right here and get the answer. But we also have 7.8 kilograms over in there. So we can, actually, no, I'm going to do it that way. All right, so 12.53 moles of the solute. Let's just figure out how many moles of solute there are by doing our math and our dimensional analysis. So we get 10 times 12.53. We get that there are 125.3 moles of this solute. But that's how many moles there are. What's the mass available to us? 7.8 kilograms. So you can do dimensional analysis again, and effectively you'll get this. This is an important number, but it's not our answer. Remember, molar mass is grams per mole. The units literally tell you what to do. It says divide the mass in grams by the moles. We have the mass, it's just not in kilograms, or it's just not in grams. So the first step that I'm going to do here for our second part of dimensional analysis, I'll do it in green, is I'm going to take my 7.8 kilograms and convert it from kilograms to grams. And we know there's 1,000 grams in 1 kilogram. And this is for the solute, by the way. This is all about the solute. So we're taking this 7.8 kilograms and converting it to grams. So far, that would actually be a really easy thing to do, because that would be equal to 7,800 grams of the solute. And hopefully you kind of see what's going on here, because we have the mass of the solute in grams, so that's going to give us all of our numerators as our possible answer choices, and then we have the moles of the solute, which is all the denominators. And if you divide, you actually get your answer. To calculate molar mass, you literally divide the mass of that thing by the moles of that thing. And that's why you get this answer. 7,800 divided by this gives you the molar mass. So move this around. So the molar mass, capital MM is what I do, is equal to this. That's why the units are going to make sense. And when you do the math, you get that answer. 7,800 divided by 125.3. Which of the following ions has the largest enthalpy of hydration? So for this one, you'll basically need to just remember from your class notes that there are two things going on here. You have radius and you have charge. Something will have a higher hydration enthalpy if it has a smaller radius and a greater charge. So we're looking for a small radius and a greater charge. So there's actually two things you got to look at here. The sulfate ion is large, so this is large. And then if you're looking just at the sizes, you have large, cesium is really large. You also have strontium, which is relatively large. I mean, these are all relative, right? So you have largish things, and then you have some of the smaller ions. This is smaller, and this is smaller. So we are looking for small radius. That means we need to basically eliminate the big stuff. We also are looking for a greater charge, and that basically just leaves magnesium as your answer because it basically has the greatest density of charge, as it packs the greatest amount of charge in the smallest amount of space. Therefore, it's going to have the larger enthalpy of hydration.